Hello everyone, welcome to SVIT channel. In this video, we will be going to learn about multi-carrier modulation. I am your course instructor, Professor S. Manjunatha Chari, Assistant Professor, Department of ECE, Sai Vidya Institute of Technology. Yes, in this video, we will be going to learn, as I said, multi-carrier modulation. We will be going to see about OFDM Basics and OFDM in LTE, how it is implemented. Before going into an OFDM, we will see the key features of LTE. Yes, the LTE is nothing but long-term evolution. Yes, this can also be called as an 3GPP, that is third generation partnership project, which was released on August 2009. Initially it has developed as 3.9G, or we can say it as an before the release it has named as an 3.9G, whereas now it is sold as an 4G, or it is providing a service as an 4G network. In this technology there are many different frequency bands for usage for mobile communication as well as in data communication. Yes, those are 700 MHz, 1500 MHz, 1700, 2100 and 2600 MHz. This is the bandwidth it is using. Yes, this is the complete bandwidth at which the LTE is operating. Yes, as I said, here we have different bandwidths. Again, in that bandwidths we can take or we can make an narrow channels with different megahertz frequencies. Yes, it is flexible to do it. Yes, which are the flexible channels over here is 1.4, 3, 5, 10, 15 and 20 megahertz of narrow channels can be created, and it can be flexible with any of the bandwidths which we have mentioned over here. And here it uses frequency division duplexing and time division duplexing, or we can be implemented both at a time, or it can be different. And it supports 4x4 multiple input multiple output functionality and beamforming in downlink. And coming on to data rates, yes, it is a theoretical values we are going to discuss over here. It is almost 326 Mbps for downlink and 86 Mbps for uplink when it is using 4x4 MIMO at 20 MHz frequency or 20 MHz channel. And modulation techniques used here is OFDM with QPSK, 16 QAM or 64 QAM it is used. Generally here you are using for lower bandwidths it is an, or lower bit rates it is an QPSK, OFDM with QPSK. For higher data rates it is an OFDM with 64 QAM technique it is used. And the technologies it is used for uplink and downlink are, for downlink it is an OFDMA, for uplink it is single carrier frequency division multiple axis. What are the differences between OFDMA and single carrier FDMA, why it is moving on to this, we will be going to see in further slides. And for error correction and detection we are using hybrid ARQ protocol or hybrid ARQ transmission. And frame sizes we are used is 10 millisecond and 1 millisecond. It can be either of one we can use. Here we have a faster feedback and better efficiency at high speeds, and persistent to the scheduled for an transmission for lower bitrate transmission. And the architecture here used for 4G LTE is IP based flat network architecture. What it is we will see in the next slides. Yes, moving on to OFDM basics. In OFDM we are using FFT, that is fast Fourier transform, to achieve LRF radio paths, or we we can say it as an L subcarriers for a transmitter as well as a receiver. Here IFT also used to create orthogonal subcarriers using just a single radio frequency. Yes, how it is done we will see. Yes, before that, how the transmission of data is done over here we will see it. Yes, when we have a data stream of L data symbols, then the time required to transmit the data will be equals to L into T. That is the total time is required to transmit. When we introduce a guard bands or a guard time, which acts as a buffer time between two OFDM symbols, you can observe over here. Here it is acting as a guard bands or a buffer between two OFDM symbols, so that it can avoid an inter-symbol interference in the OFDM. And moreover, you can observe once it is at the transmitting end, when receiving at the receiver, you can observe the time of a guard band is increased comparatively. Over here you can see that it is increased. This is called as a delay spread. So that because of the delay spread, there will not be much interference of OFDM symbols. In the last slide, we have learnt about guard bands. These guard bands acts as a buffer region or guard interval to protect OFDM signals towards ISI, that is inter-symbol interference. In this OFDM, we are using cyclic prefix as a guard bands. As you can observe over here, how we use or how you calculate the cyclic prefix code over here. As we discussed in the last slide, OFDM data symbols will have a length of L bits. This is the OFDM data symbols. Here we will be going to take V symbols from that L symbols. You can observe here, this is a V symbols from the entire OFDM L symbols I am taking over here, or I am copying this part and I am going to paste the same symbols at the front of the OFDM data symbols. This is how we are going to take and or copy and the symbols of OFDM as a cyclic prefix in each and every OFDM data symbols. These OFDM symbols are independent and it avoids ISI and ICI, that is inter-symbol interference and inter-channel interference. Here the V is the length of cyclic prefix. It should be equal to, at least equal to channel order. This cyclic prefix performs mainly two functions. As I said in the last slide, here it eliminates ISI by using guard intervals, and at the end it repeats the end of the symbol, so the linear convolution of frequency selective multipath can be modeled as a circular convolution, which in turn may transform the frequency domain via DFT. By using this, we can estimate channel and also equalization. Yes, next topic is OFDM block diagram. You can observe over here, as we discussed earlier slides, we will be going to send an L data lines over here. Before going to that, you can observe from this point to this point or up to this point, it will be in a frequency domain, whereas this dotted lines indicates it will be in a time domain. Yes, the conversion is done over here, and here we will be using L point DFT in order to convert from frequency domain to time domain, and we are using parallel to serial converters so that we can add CP easily with the codes, and here impulse response also included, and this part up to here it is an transmitter part, this is an receiver part. In the next slide we will see what is the exact function of each and every block over this. First we will see about the transmitter operation. In OFDM, the wide band signal of bandwidth B break into or sliced into L narrowband subcarriers of each bandwidth as an B divided by L, and each subcarriers will experience flat fading or ISI free communication by implementing cyclic prefix so that it have a delay spread, and all L subcarriers are given with OFDM symbols with represented as a capital X as a vector, and here L independent narrowband carriers are created using IFFT operation, and here all IFT or FFT decomposed ISI channels will undergo orthogonal frequency subcarrier technique. A cyclic prefix is used to append with IFT operation, resulting L plus V symbols are then sent through serial wideband channel. Yes, in this slide we will see what is a receiver operation. Yes, at the receiver the cyclic prefix added in the transmitter side will be discarded first, and whatever the L symbols received will be demodulated by using FFT operation, and which results only L data bits. Over here you can see the equation will be using at the transmitter and the receiver side. We will be going to get it like this: y equals to L, which is equals to h of L into XL plus NL. Here L is a subcarriers, and each and every subcarrier will have a different impulse response, and in each and every channel we will be having the OFDM symbols, and in turn it will be added up with the noise. So we will be going to use frequency equalizers at the end in order to get the complex channel gain, that is h of I, for the subcarriers. Yes, moving on to OFDM in LTE. Yes, the OFDM will be implemented in LTE in time domain as well as some frequency domain interpretations. Yes, here you can see the modulation technique used over here is the QAM symbols over here. You can observe, as we discussed in the last case, we will be going to send a baseband signal of bandwidth B, and it is converted as an or sliced as an narrowband signals of bandwidth B by L. You can observe over here, and we are working as an or implementing IFT, and here we will be having a prefix over here appended over here, you can observe, and which makes LG. Here you can observe this is an LG of cyclic prefix, plus here L is an data lines, here L is a data lines, which gives an L into 1 plus G samples over here, and this is converted into digital to analog over here, and here we are using exponential of j omega c. This is an analog multi carrier, it is modulated over here and it is transmitted. In the last slide we have seen the block diagram of OFDM in LTE. Over there you can observe that there was an L data symbols with an serial to parallel converter which supports the symbol mapper, and here we have used L point IIFT to create time domain L vector so that it can be extended up to L into 1 plus G, where G acts as a fractional over 8. Normally in LTE we use 0.07 as a normal cyclic prefix, and it can be extended up to 0.25, and here we will be used a parallel to serial converter into wideband signal, so that amplitude modulation can be done with a radio or with a single radio carrier, that is Fc equals to Wc divided by 2 pi. And we will see what is a here we will calculate a data rate of a channel with 10 megahertz, and the modulation technique used is 16 QAM, and when we are using 16 QAM, M becomes 16 over here with nominal cyclic prefix, and we have a formula is R equals to B by L, LD log of 2 into M divided by 1 plus G. Here B is transmission bandwidth, L indicates number of subcarriers, this LD indicates data subscribers, here M is the type of modulation we are using, that is 16, 1 plus G. G here it is a normal cyclic prefix. So we are going to substitute each and every value over here. This B is 10 megahertz as I said. This 10 megahertz can be written as an 10 to the power of 7 megahertz into the LD is number of data carriers, that is 600. Here 600 we have written log base 2 of 16, this is 16 is this one, divided by the L is number of subscribers, that is 1024, and this 1 plus G, G is a guard band or cyclic prefix, that is 0.07 for a normal cyclic prefix. So it becomes 1 plus 0.7 is 1.07. If we are calculating this one with the help of scientific calculator, it will be of 21.9 Mbps. That is a data rate at 10 megahertz with 1024 subcarriers or a number of subscribers. Thank you for watching this video.